Let's jump to our next kind of topic here. We can't really talk about groups without also talking about homomorphisms. We defined what a homomorphism was in the context of working with graphs. When we're working with groups, a homomorphism is, well, first it's a function, and it is a function that sort of preserves the operation. So here I'm being really general. So G is a group, and its operation I'm just writing as the dot, like multiplication. And H is a group, and it might have another operation, right? I'm just going to label that star. And phi is a function. That's our homomorphism. Phi maps from G to H. So phi is a function where I can plug stuff in G, and it sends me over to H. And it has to have the property that if I find phi of x times y, so x and y are elements in G, and if I smash them together first in G and then send the product over through the function, that will give me the same result as if I send each x and y over to H individually and then perform the operation in H. Right? So what's really important here is this is the operation in G, and this is the operation in H. If a homomorphism is one-to-one, you might call it a monomorphism. I don't think that term is used super often, but you might see it depending on what resources or other books you look at. If it's onto, we might call it an Epi Morphism. Remember that another word for being onto is that it could be the function would be called epic. And if a homomorphism is both one-to-one and onto, then the function is called an isomorphism. And if G and H are isomorphic, we use this symbol right here. It's like an equals with a little squiggle on top. So let's take some groups, we'll define some functions and try to figure out if we have homomorphisms. So let's say we look at the group of rational numbers under addition. So our operation is addition, and so we know that the identity element is 0, and inverses exist because they're just going to be the negatives. And we're going to define a function from the rationals to itself, so it's the same group now, and we're going to send any rational number x to twice its value. So x maps to 2x for any rational number. We want to know, is phi a homomorphism? So we need to check the following. Is phi of x plus y equal to phi of x plus phi of y? Because it's the group to itself, the operation is addition on both sides. So let's do that. Let's check. Let's find phi of x plus y. Okay, well, yeah, hold on a second. This happened earlier today. Gotta love Adobe sometimes. Okay, so we need to check if this is true. So now let's work with phi of x plus y. This function, I'm just going to use how the function's defined here. Phi of x is 2x. So whatever the input is, we're going to double it. So we know that this is 2 times x plus y. Now these are operations. This is an expression where x and y are just rational numbers. We have 2 times multiplied by, x plus y. Regular algebra prevails here, so we know that we can distribute 2x plus 2y. And the thing we want to observe right now is 2x. Well, 2x, that is the same thing as phi of x. And 2y is the same thing as phi of y. And so these are, in fact, equal. And this means that phi is a homomorphism. How's that so far? All right, so now what we're going to do is change this just slightly. The function's the same. Phi of x is 2x. But now we're going to consider the rational numbers under multiplication. And I guess I should probably change this to just the positive rationals, because we know that 0 does not have an inverse. So if we want to be precise here. So we're changing the operation in this group to multiplication, right? So now the identity element is 1. We know that the inverse of an element is just the reciprocal instead of its negative. And we're going to define our function in the same way. Now is phi a homomorphism? Again, we need to check is phi of x times y equal to phi of x times phi of y. Our operation in the group changed. It's still from the group to itself, so we have the same operation on both sides, but that operation has changed to multiplication. Well, let's find phi of xy. The function's the same. The function says whatever you plug in, just double it. So this is 2xy. But on the other hand, if we find phi of x times phi of y, we get, well, phi of x is 2x, and phi of y is 2y, and this gives us 4xy. These are, in fact, not equal. And because we got different results when we found phi of x times y versus phi of x times phi of y, they did not give us the same result. That means in this case, phi is not a homomorphism. Okay, so far? Let's look at one more example. In both of these examples, our groups were the same. You know, we had a function from a group to itself. In example 612, we're going to define a function between two different groups. So we start off with the set of all real numbers under addition. So that's our group G. Our other group is going to be just the set of positive numbers under multiplication. And we're going to define our function phi by phi of x is equal to e to the x. And we want to know, is phi a homomorphism? So again, we need to check this property. Is phi of, now I'm going to make sure it's mapping from G, and that operation is addition. So phi of x plus y, that's the operation inside the function. Is this equal to our other, the group H, the operation is multiplication, so is this equal to phi of x times phi of y? So let's check it out. Let's find phi of x plus y. Again, what we have, x and y are just real numbers. Any real numbers. They could be positive, negative, whatever. What does the function, what should we get when we plug the sum x plus y into the function?
to the x plus y.
Uh-huh. Right, so we just raise that sum up as a power on e. But we're adding inside the exponent. So how can we rewrite that?
It'd be e to the x plus e to the y.
Nope. When we add exponents, we usually use this property in the reverse order. What is it that allows us to add exponents?
Other than if it was the same base, but is it
It does have to be the same base, yeah, but what's the operation got to be?
multiplication?
Uh-huh, yep. So this is e to the x times e to the y. And usually, you know, if we were going the other way, if I said, what's e to the x times e to the y, I think everybody would immediately just say, oh, that's e to the x plus y. And we're kind of used to using that property in the other order, in the other direction. So, yeah, just rules of exponents. We know that e to the x plus y is the same as e to the x plus, times e to the y. But now e to the x, that's phi of x. And e to the y is phi of y. So in fact, these are equal. And so phi is a homomorphism. Now we're going to go through, kind of establish a bunch of results. We'll prove a couple of them. The 612 and 613. So 612 says the identity gets mapped to the identity. If I have a homomorphism, if phi is a homomorphism, and if 1 is the identity in G, then phi of 1 is the identity in H. And actually, let's check this up here. What is the identity element in the G group? That's a group under addition.
0.
Yeah, so our one element in G is 0. And what's the identity element in the H group?
1.
Yeah. So the one element in H is 1. So if we find phi of 0, that's e to the 0, and what's e to the 0? It's 1, yeah. Any non-zero base to the 0 power is 1. So here we have the identity in G, right, being mapped to the identity in H. Not only does it map the identity to the identity, but it maps inverses to inverses. So if we have an element G, right, its inverse is G inverse. When you throw that into the phi, into a homomorphism phi, it maps it to the inverse of phi of G. So let's think about what that looks like up here. Let's say we take the element 2 is in our G group, right, is in the real numbers. And the inverse of 2, because this is a group under addition, let me actually include that. The inverse of 2 is negative 2, because our identity is 0. So phi of negative 2 is e to the minus 2, which is the same as 1 over e squared. But 1 over e squared is the inverse of e squared in the H group, right? Because in that group, the operation was multiplication, so the identity is 1. All right, so the inverse of e squared would have to be 1 over e squared. So we could sort of see this happening as an example, just looking at this particular homomorphism. What these results are saying is that that is always true. A homomorphism will always map the identity to the identity, and it will always map inverses to inverses. Let's establish this next one. This is one really about subgroups and not so much about individual elements. So let's say we have a homomorphism, and from G to H, and K is a subgroup of H. Then what we're going to show is that the inverse, not the inverse, the pullback, the preimage of K is a subgroup of G. We know, by the way, that the preimage would have to be contained in G. It would have to at least be a subset. But we're going to show that it is, in fact, a subgroup of G. So here's what we need to show. We spent a bunch of time last class establishing that subgroup criterion, right? That sort of one-stop shopping to show that something is a subgroup. So what we need to show is that for all x, y in K, in the preimage of K, then x times y inverse is in the preimage of K. So we've got these couple of elements, right? X and y are in the preimage of K. So let's start there. If x is in the preimage of K, that means that phi of x has to be in K. That's what it means to be in the preimage. And likewise for y. The other thing we know is that K is a subgroup of H. So now that we have these elements in K, phi of x and phi of y, they're elements of K, we know that K is a subgroup of H. Then we can use that subgroup criterion on those elements. So that means that phi of x times the inverse of phi of y has to be an element of K. Now we're going to get to use the fact that phi is a homomorphism and those two previous results. We said in a homomorphism that it maps inverses to inverses. So that means that this element here, the inverse of phi of y, that's the same as phi of the inverse of y. Can anybody see where we might go next? Guesses are fine. Using the fact that phi is a homomorphism, what does that allow me to do with this expression? Let's go back to that definition of a homomorphism on the last page. And it's just this first part. We don't know that our function is one-to-one or onto or anything.
Because of the way we have it set up, which is like phi of x times phi of y inverse, we can set it up as phi of x times y inverse.
Yeah. We can perform the operation inside the function itself, right? So this product that we have is the same as phi of x, y inverse. That's because phi is a homomorphism. In fact, both of the last steps, just using the fact that phi is a homomorphism. This is just the definition of a homomorphism that we used. And if phi of x times y inverse is in K, then that is exactly what it means to say that x times y inverse is in the preimage of K. And that's what we needed to show. That's what we set up here, right? Like this was our goal. And we did it. So we know that the preimage of K is a subgroup of G. So spending that time, establishing that the subgroup criterion theorem about the fact that this is all we need to show in order to say something as a subgroup actually saves us time. We didn't have to check specifically for closure or specifically for inverses or specifically for the associative property. It is just our kind of one-stop shopping, I guess, to show that we have a subgroup. This property, we said that if we have a subgroup in H, like if I were to sort of sketch out this relationship here, so we have a group G, and we have some function phi, right? That's a homomorphism of groups here, and then we have K, which is a subgroup of H. What we're saying is that if I look at the preimage of K, that is also a subgroup of G. But this works the same way. This works in the other direction, I should say. If I have a subgroup of G and I apply the homomorphism to it, then its image will be a subgroup of H. And that's what our next result says. We won't prove that one, but that's basically what theorem 615 says. If I have a homomorphism from G to H, and I have if K is a subgroup of G, then if I find phi of K, that will be a subgroup of H. So a homomorphism really kind of preserves a structure in a group, in much the same way that it preserved relations in a graph, right? We said a function between two graphs was a homomorphism if it kind of preserved edges between two vertices. If they were connected in one graph, they still had to be connected in another graph. Here with groups, we kind of are preserving a similar kind of structure. This next definition just tells us how we can make new sets from old sets. So if I have a couple of subsets of G, they don't have to be subgroups, then I can find the product HK just by taking all the different, any element of H and smashing it together with elements of K, do that in all the ways that we can, and that'll produce another set. If we do that, then if we did that, say, with 3 subsets, then that operation is associative. This doesn't say that element for element they're all the same, but it just says we produce the same set overall. And now we get to kind of a big definition. If H is a subgroup of G, not just a subset, if it has the property that when I find this set, meaning for every element in G, I just take that element, I compute G times H times G inverse for all elements of H. I kind of produce that set. And as I do that, I just keep producing H, right? Like it doesn't send me outside the group. So I could find, pick an element of G, I take G times every element of H times G inverse, and it won't send me outside the set. If that's the case, then we say that H is a normal subgroup. Notice it doesn't say that GHG inverse has to give me just the same element for every element, right? But it won't send me outside the set overall. I'll stay inside. Another way of writing that is that if I find G times H as a set, so I produce this set, that will give me the same set as H times G. Sometimes people read this definition and they kind of mistake it for being abelian, but we're not saying that the operation is commutative. We're not saying that any time I find a product G times a little h, that that's the same as little h times G element for element. What it's saying is that I will produce the same set of elements. If this is the case, we call H a normal subgroup, and we change ever so slightly the notation. Instead of just the less than or equal sign, we kind of close off the triangle, and that means that it's a normal subgroup. We're going to work more with normal subgroups. Normal subgroups in group theory are an incredibly important concept, and we're going to kind of get our feet wet actually working with some subgroups and showing that they're normal and actually kind of playing around with this operation that we're just describing. For now, I'm going to do kind of just go through one more definition, and we'll establish another result, and then we'll leave the rest for Monday. So if I have a homomorphism between groups, then the kernel of phi, the kernel of the homomorphism, is the set of all the elements that map to the identity. Notice that a homomorphism need not be surjective in itself. It need not be one-to-one. So it's possible to have a bunch of elements that do map to the identity. Like, that's okay. When that's the case, or when we consider all the elements that map to the identity, we call that the kernel of the homomorphism. And as it happens, the kernel of a homomorphism is a normal subgroup of G. So we're going to show, we're going to prove theorem 617. We're going to show it's a normal subgroup, so actually we need to first show that it is a subgroup, and then we'll show that it's normal. So let's begin. So we're going to show that the kernel of phi is a subgroup of G. And again, we can use that that subgroup criterion. So what I'm going to do is just pick a couple of elements that are in the kernel. So let's suppose that H and K are elements of the kernel of phi. All that we know about these elements is that under the phi function, under that homomorphism, they map to the identity in H. That's basically all we know. And we're going to show that HK inverse is in the kernel. So we want to show that the product HK inverse also maps to the identity. So let's look at phi of HK inverse. We're hoping to show that that is equal to 1 in H. Phi is a homomorphism, though. That means that we can split this up, that this has to be the same as phi of H times phi of K inverse. And again, because it's a homomorphism, the phi of K inverse is the inverse of phi of K. But here's the one thing we know about, like if H and K are in the kernel, we know they map to the identity in H. Like, that is the one thing we know about them. So we know that phi of H has to be 1. In H has to be our H identity. So this is 1. I'll denote that as 1 sub H times. And phi of K also has to map to 1. So this is the inverse of 1 of our identity. The inverse of the identity is always just the identity. The identity is the element that is its own inverse, or one element that is its own inverse. So This just gives me 1 times 1, which is 1. So this means that HK inverse is in the kernel of phi. That's enough for us to conclude that phi of k, phi of the kernel of phi. Let me let me get my words back. This is enough for us to show that the kernel of phi is a subgroup. Now we need only show that it's normal. So let's grab an element of G. Let's let G be an element of G and K be an element of the kernel of phi. What we want to show, what we need to show, that G times little k times G inverse is just an element of the kernel of phi. What that means is, because all I've done is assume that G is any old element of the group G and K is any old element of the kernel, if I can establish that this arbitrary, product that we're finding has to be contained in the kernel, that means that as a set, that this would be contained in, this would just give me the same elements as the kernel of phi. So we just need to sort of show this containment here. And if we want to show that that's in the kernel, what we need to show is that it matches to the identity. That's what it means to be in the kernel of a homomorphism. So let's find phi of, I guess I had a little bit more space than I thought. Let's find phi of that product, G, K, G inverse. Again, phi is a homomorphism. So the first thing we can do is just sort of split this up. I know that's going to be the same as phi of G times phi of K times phi of G inverse. And of course, phi of G inverse has to be the inverse of phi of G. Now, the last time on the other side, we had, all of our elements were in the kernel, so we know these all had to go to the identity. But over here, G is any old element of G, right? I don't know where G maps to, but I do know that K is in the kernel. So phi of K has to be 1. But of course, multiplying something by 1, it's the identity element, doesn't change anything. So that actually means that this product is the same as phi of G times phi of G inverse. And what is that going to give me? Yeah, that's the identity. I multiplied an element by its inverse. That's the identity in H. And so that means that this is in the kernel. And now I really am running out of room. The kernel of phi is in fact normal subgroup of G. Note to self, I'll leave a little bit more space for this and then for the next time around. So we covered a lot of ground today, and just this whole concept of what a homomorphism is and what it means to be a normal subgroup. We're going to explore more with that on Monday. I appreciate you giving me an extra 4 minutes today. And I hope you all have a good weekend. Reach out with questions that you might have on Assignment 9. We had spent a bit of time working with homomorphisms, kind of getting the feel for what a homomorphism is, and then we defined the kernel of a homomorphism, and we even showed that the kernel of a homomorphism is a normal subgroup, not just a subgroup, but is in fact a normal subgroup. And you might recall that the kernel of a homomorphism is just all the stuff that maps to the identity. So if phi maps, if we have a homomorphism that maps from G to H, then the kernel of phi is all the G elements that map to the identity in H. So we're going to examine why we kind of care about normal subgroups, and we'll do so mostly by examining a particular group we call a dihedral group. It's sort of a class of groups. There's lots of different dihedral groups. So you might recall that a normal subgroup we defined as being, we'd said H was a normal subgroup if G times the set H is equal to H times the set G for every element G in G. Now that doesn't mean that the operation itself is commutative, right? Like that's not what normal means. It's not saying that on an element by element comparison that you get the same thing. It just means that these, which are sets, they're the left and right cosets, that you generate the same set of elements. If you take a subgroup H and then take elements of G and just sort of combine them with elements of H and see what sets you produce, those cosets, that it doesn't matter, that you will produce the same elements even if you find the right cosets. Or you'll produce the same, you'll produce the same elements in the set. So if G is abelian, then all subgroups are normal, because if G is abelian, then this is in fact true, and of course then that would hold on a set basis. So for example, if we scroll back, where did we? Oh, it must have been. We found cosets. Let me find the example. Oh yeah, okay. So here we found the left cosets. We said that Z under addition was a group, and that it had a subgroup 5Z, all the multiples of 5. That was also a group under addition, so it's a subgroup of the integers, and we found the left cosets. If we had found the right cosets, like instead of finding 0 plus H, if we found H plus 0, that would generate the same set that we got here. So the integers under addition, that's an abelian group anyway, right? The operation itself is commutative. So it's no surprise that when I reverse the order here, I'm going to produce the same set. What we're saying is that the group itself need not be abelian in order to have normal subgroups. And we'll examine that in a little bit more detail once we learn about the dihedral group, because we have not yet encountered a group that is not abelian, right? We've looked at the integers under addition, or the integers under multiplication, or positive rationals under multiplication, and those are all those operations are commutative. So all of the groups we've seen so far are abelian. So here's our first look at a non-abelian group. This is a dihedral group of order 8, and here's what we're going to start off doing. So imagine we have a square. This is essentially, we're going to look at the set of symmetries of this square. So we're going to imagine what are all the ways that we could maybe pick up this square, do something to it, and put it down again so that it fits in the same outline. And how many ways could we do that? We call these the symmetries of the square. So let's start by, say, numbering these corners. This is a little bit, I think, better to do if you actually have physical squares, but given that we're doing this over telepresence, that's harder to do. So I'm going to ask you to kind of sort of bear with me with this, and I'm going to draw lots of squares, and we're trying to see what we get. Now, one way that we could adjust the square, right, find a symmetry of the square, would be to, say, rotate 90 degrees. If I rotate 90 degrees, and we'll say clockwise. If I rotate 90 degrees clockwise, well then that would just send, I'll write these same positions in red. So that would send the 1 down here, and the 2 would be down here, and 3, and then 4. Right? We're just sort of rotating it 90 degrees clockwise. Notice that 45 degrees clockwise would not be a symmetry because it wouldn't fit in the same spot. Right? It has to be 90 or 180 or 270 or back to its starting point, 360. So how many rotations do we have? Like, how many times could we rotate this and be able to put it back to where we started?
It'd be 3 times before you get back to where you started.
Yeah, so I would say then that means that we have 4 altogether, because one option is to do nothing. Right, so I'll even, it might seem like I'm cheating a little bit, but I'm going to include that as one of the rotations. Right, so we have 4 rotations. And they are 0 degrees, 90 degrees, 270, and, oh, whoops, I skipped one. 180, 270, there we go. And of course the 0 degrees is the same as 360. I could keep rotating, but I'm not going to generate new symmetries beyond these 4. So there's 4 positions I could rotate it. The other way we could change and find a new symmetry is if we flip it over. Like, and you could choose, there's more than one, kind of axis of symmetry you could choose. I've chosen to draw this line that goes from the bottom left to the top right. So now, let's say we do a flip. And what I'll do is I'll just flip it across this dotted line, and I'll do this in green. If I flip across this dotted line, the 1 stays exactly where it is, and so does the 3. Right? Those guys don't move. The only thing that changes is that the 2 and the 4 change. Oops. And you'll notice that is not a rotation that we would get by one of the that we would get by one of these rotations. Like that, it legitimately gives us a different symmetry of the square than just the 4 rotations. But when I combine flips with rotations, right? So I've got the 4 rotations with the square as it is, but then I could flip it, and then I get 4 more rotations, right? So we can combine rotations with flips. And this, it might not seem intuitive at all, but is a group. The set of rotations of the square, the set of symmetries of the square, does in fact form a group. And we're going to examine that in some depth today. So this is a dihedral group of order 8. Because it's order 8 because I've got 4 rotations, but then I could flip it and then I get 4 more rotations there. Right, so that's a total of 8 kind of symmetries of the square. So it's a dihedral group of order 8, which we'll denote with a D8. We could also examine symmetries of the triangle. We'll have rotations of the triangle and a flip as well, and that's D6. In fact, you could look at rotations of any polygon with 8 sides, as long as it's like a regular polygon with 8 sides. And you'll have a dihedral group of order 2n, if there are n sides. So the elements, we need a way to kind of have a bit of a shorthand for these symmetries. We kind of have described in English what we're doing. So we'll let the identity element will just be leaving the square where it is. Do nothing. And that's our 1. That's our identity element. Then we have these rotations. So we'll let R be a 90-degree rotation clockwise. If I compose R with itself, if I do it again, that would be the 180 degrees and so on. So we'll call that R squared and R to the R cubed. And then, of course, if we do a rotation 4 times, we get 1. So these are the distinct rotations, 4 distinct rotations. But knowing that when I do the rotation 4 times, we get the identity, one thing we could observe is that the element R has order 4. The inverse of the rotation, so imagine, here's my square. My rotation is clockwise. So if I go backwards, right, R inverse, that's going to be a counterclockwise rotation. And so it'd be 1, 2, 3, 4. But that's the same thing I get if I rotate three times clockwise. So the rotation has an inverse. Let's go back to this set of this original square. We said that we're going to, when we flip it, that we're just going to flip it across this axis of symmetry. What is the inverse of a flip? Like, what should be the inverse element of a flip? Like, for example, let me erase some of these. So here's our original position. If I flip, then the 1 and the 3 stayed where they were, but the 4 and the 2 swapped, right? What is an operation I can do that undoes that operation, that puts things back into the 1, 2, 3, 4 position?
Just flip it again.
Flip it again, yeah. So the flip is its own inverse. In that sense, we could observe that a flip is an element of order 2. So we're going to denote the flip as the element S. I guess I didn't really list that here. So S will be our flip. And S squared is 1. Right, if I want to undo the flip, I just flip again. Oh yeah, there we go. I did write it down. So right now we have ways to denote the 4 rotations and a single flip. That's 5 elements. But the other elements we get by we obtain by composing them with each other. So if we list out the elements, we have 1, and then we have all these rotations. There's our flip, so those are the 5 elements we have so far. But then we get all the other rotations with that flip. So we have SR, SR squared, and SR cubed. And the order here in which we execute these operations is important. So SR denotes a rotation followed by a flip. So the one that's innermost, SR, means we do the rotation first and then we move out to do the flip. So one quick question is RS the same as SR? And they're in fact not the same, and I'm going to try to convince us of that. And so I'm going to, I'm going to draw a bunch of squares here, so I hope hope you could bear with me. So here's a square in the original position. 1, 2, 3, 4. We're first going to find our SR. So we're going to do the rotation first, and this is a rotation counterclockwise. So then this becomes 1, 2, 3, 4. And then we'll perform the flip. So I'm flipping it across this line, so the 2 and the 4 stay where they are, and then the 3 and the 1 switch. So this guy right here, this is the result of SR. Now let's do it in the other order. 1, 2, 3, 4. Let's do a flip first. That leaves 1 and 3 in their positions, but we flip the 4 and the 2. And now we'll rotate clockwise 90 degrees. And so that leaves us with 1, 4, 3, 2. So this is RS. Yeah, that looks right. And you know what? Can you guys forgive me one? Forgive the error I just made. I just did these rotations in the counterclockwise direction, and I wanna be consistent with what I did before, with how we defined them. So rather than lead you astray, I'm gonna just stop and correct myself. This one I don't need to change. So when we do a flip, when we do the rotation first, we get 2, 1, 4, 3. That's better. That should be in keeping with what we did. And then when we flip across, we have 1, 3, and then 4, 2. That's better. Next, when we flip, this part stays the same, and then when we rotate clockwise, we have 1, 2, 1, 2, 3, 4. There we go. So still, the observation holds in that these are not the same. Yeah, but that's the point. They're not the same. They only produce the same result if all the numbers all the corners end up in the same position. So the fact that they aren't, I mean, by that logic, r and r squared would be the same if you just rotate it once more, right? So these are, these corners do end up in different locations, which is how we know they're not the same. Now, what we're going to try to do is figure out what is RS equal to, because the way we've written out these operations, we wrote them as SR, SR squared, SR cubed. So we know that RS is not equal to SR, but is RS a new element that we didn't write down? Or is it another one? I mean, it seems like it should already be accounted for here, because it's still one of the operations. I mean, physically, there's only 8 positions, right, that you can get when you either rotate or flip the square. So let's show that in fact RS is really equal to the same thing as SR inverse. So if we find the R inverse first, R inverse will be a counterclockwise. So now I really am going to do the counterclockwise. So we have 1, 2, 3, 4. And now we will flip it across this. So 4 and 2 stay where they are, and we flip the 1 and the 3, and these are the same. So in fact, RS is the same as SR inverse. SR inverse, doing a counterclockwise rotation, is the same as doing a clockwise rotation 3 times. And so this is in fact the same as SR cubed. So this operation is already in our set right here. This observation, the fact that that RS is the same as SR inverse, which is the same as SR cubed, that tells us how we can rearrange the order of those operations. Like if I want to put my R's in the front and my S's after, then I can do that. I can flip these as long as I make sure that I swap the R with its inverse. And that's really helpful in finding compositions of elements. So let's find some compositions. So here, we're going to perform a rotation and then compose that with a rotation followed by a flip. It's fine to use the multiplication notation. Depending on the book you use, they might use the circle instead, but we kind of are adhering to that multiplication notation, especially when we use R and R squared and R cubed. So here I've got SR squared. Right, I just compose the rotation with the other rotation, and I bring down that S. That's one of the elements, the 8 elements in the group. Now this is where it starts to get tricky, and we need to remember how do we flip these. So I've got SR squared SR. I know how rotations work together, and I know how flips work together. Right, a flip with a flip is just they annihilate each other because it's its own inverse. And I know how rotations work together. So what I want to be able to do is flip these guys, and I can do that. SR is the same as, I know I can flip these if I replace the R with its inverse, which is R cubed. And R squared times R cubed, what should that give us? Guesses are fine. Like it, even if we don't have the final answer yet. But what would it look like? Yeah, because I rotate twice and then I rotate 3 more times. So in one sense we could say, well, this is R to the 5th, right, rotating 5 times. But of course, there's only 4 rotations. I mean, as soon as I get to R to the 4th, that's the identity, and I rotate once more, and so this is SR times S. And now we're going to flip these one more time. These last 2, I can replace RS with SR cubed. And what's S times S? Yeah, that's just 1. That's just the identity. So we just get R cubed. And there's one of our 8 elements in the set. Let's try another one. SR cubed times S. Again, I want to kind of, be able to flip these around because I know how R's commute with each. I know that R's do commute with each other, right? A rotation followed by a rotation, and I know how the S's compute with each other, how they are composed. So let's flip these. This R cubed times S. What am I going to replace that with? Yes, SR. Yeah, exactly. So I can flip these, but I have to replace the R cubed with its inverse, and the inverse of R cubed is R. Think about the inverse as something that gets you back to the identity. So if I have rotated 3 times, the way I get back to the identity is to rotate once more, right? So I can flip them, and R cubed S becomes SR, and S times S, like in the last example, That's just 1. And so this becomes R. These, these operations that we're learning, it definitely takes some getting used to. But the basic idea is that if you want to flip the S and the R, you can do so as long as you replace the R with its inverse. R is composed with R's, and S squared is 1. So if we kind of get used to that, then these become a little bit easier. So let's try one more. SR cubed, SR cubed. Again, I want the R's to be next to each other or the S's to be next to each other. I've usually done this by like choosing the last pair to rotate, but you could really pick whatever pair of values you want to. What's something we could do here?
Well, SR cubed is the same as RS, so like this one, for example.
Oh, like this one here?
Yeah.
Yeah. So we get RS, and then we have SR cubed. And then we have, that's helpful because we have this S times S in the middle, right? And the S times S in the middle is just 1. So this becomes R times R cubed. And what does that give us?
1.
It gives us 1, right? R to the 4th is 1. So one of the things we could observe here, we found SR cubed times SR cubed. It looks like that if I wanted, that the inverse of SR cubed is in fact SR cubed. It is its own inverse, because when I compose it with itself, I get the identity. You with you? You guys look like it's a Monday morning. It looks like it's a Monday morning. It feels like a Monday morning. Okay. Well, let's stay with me a little bit. How are we doing out in Adobe and Randolph? Are you still with me?
Yeah.
You sound really excited to be with me, but let's let's find some subgroups. Right, so we know D8 is a group. We know how the elements interact with each other. We know what our identity is, and we kind of know what inverses are. I mean, we found a lot of them anyway, and it wouldn't be hard to define what the other inverses are. So let's find these subgroups. So these are subgroups all generated by a single element. So we're going to start with, what's the subgroup generated by R? Well, we have R squared, R cubed, and once I get to another rotation, that gives me the identity. And then this would just continue, right? What about S? What elements are in this subgroup?
Just 1 and S.
Just 1 and S, because we know that S times S is 1. SR, if we compose SR with itself, SR times SR, well, let's say we flip these guys and we get R cubed S times SR. S times S is 1. So we get R cubed times R. And that's 1. So it looks like this just has 1 and SR. Let's do SR squared. So what happens when we compose SR squared with itself? Let's say if we flip the first SR squared around, what do I get if I flip those first two elements around? What is the inverse of R squared? No, 1 is only its own inverse. What's that? The inverse of r is r cubed, not, yeah. If I flip the s and the r squared. R squared, yeah. Like if I rotate twice, the way I get back to the identity is to rotate twice again. So this would be r squared s, sr squared. And again, s times s is 1. So we get r squared times r squared, which is the identity. So this has just the elements 1 and sr squared. And then our last subgroup that we're going to examine in this example is the one generated by sr cubed. Now, in the previous example, the last one we did was we saw that sr cubed times sr cubed is 1. So again, that subgroup generated by sr cubed just has those two elements. So these are all cyclic subgroups, right? Because we just generated them by a single element. We have one cyclic subgroup of order 4 with just comprised of the rotations, and then all of the 4 sr squared, and sr cubed, they generate their own subgroups of order 2. How are we doing so far? Okay. So we're just kind of learning the mechanics of these symmetries and how they interact with each other. Let's find a couple more subgroups. These ones won't be cyclic because we're going to generate them with a couple of elements. So let's start off and find the subgroup generated by the two elements s and r squared. We definitely get 1 because s times s is 1 and r squared times r squared is 1 for that matter. And we'll clearly get both s and r squared. What's another element that we'll get in this? So I have the s and the r squared elements by themselves, right? How else can I generate another element?
Do them together, like S together.
Yeah, sr squared, yeah. Put them together, right? We're generating a subgroup with these both of these elements, so we're just allowing ourselves to combine either or both of these. So sr squared. And of course, sr squared, you can check this. I'll leave this for you to check on your own if you wish, but when you combine any of these 4 elements with each other, you'll just get another element that's already in the set. So there's nothing else we can generate. S times sr squared, for example, is r squared. R squared times sr squared is just s. Sr squared times sr squared is 1, and you can work out the details if you want to see those. So there's that subgroup, and let's try this one, rs and r squared. So the first thing I'm going to do here is actually just rewrite that rs as sr cubed. Not that we have to, but we've been sort of adhering to the convention of writing the s's first. So I'm going to do that here. So what do we get in here? I mean, r squared is its own inverse, so we know we'll get the 1 identity, or the 1 element. We know that we'll have r squared and we'll have sr cubed. So we get those by themselves. Let's see what we get if we combine these two elements together. So let's say sr cubed times r squared. What should that give us? SR, yeah, because we get SR to the 5th, and of course R to the 5th is the same as R to the 1st. So there's our other element. These subgroups are interesting, and I'm going to tell you why. they're groups of order 4, kind of like, we generated that cyclic subgroup of just the rotations, and, that was also a subgroup of order 4. These are structurally different from that one. First of all, that subgroup was cyclic, and these are not. But also S r squared and SR squared, those all have order 2. They are their own inverses. R squared, SR cubed, and SR, they are their own inverses. So here we have these groups of order 4. So we have 4 elements, we have the identity, and then 3 other elements that are their own inverses. And that's kind of interesting. Questions so far? Okay. I want to do one more thing today, and we'll probably finish up this section on Monday. I know I was being a little bit ambitious when I thought we might finish it today, but so let's look at the subgroup H, which is just the group of the rotations, cyclic, right? We're going to show that H is a normal subgroup of D8. Remember that this group is not itself abelian, so it's not obvious that this group would be normal. So here's what we're going to show, is that for any element G in D8, and I'm going to use sort of the conjugation notation, a normal subgroup, one way that we defined this was that GH is equal to HG, right? That the left cosets are the same as the right cosets. But this is the same as showing that GHG inverse is equal to H. So this is the way I'm going to go about this one. So we're going to show that for any element in D8 that GHG inverse is equal to H. We call this operation conjugation. So now, one thing we could observe is that powers of R commute with each other. So we're going to bang out like 4 of these already. So if H is just consists of these elements, right? Then when I find some R to the I times H times R to the I inverse, this will always just give me H. Because in fact, H is always just one of these elements of R. The rotations commute with each other. So not only will I generate the same set, I'll in fact, element for element, generate the same element. It's kind of like the one we looked at before where we had the multiples of 5 as a subgroup of the integers as a whole. So I'm not going to like show out that conjugation. We're gonna do a more interesting example. So that takes care of the rotations themselves. Now we'll look at what if we take the element S. And we'll note, what is the inverse of the S element? Say that again? S, yeah. So if I take S times 1 times S, because S inverse is equal to S, what does that give me? Not a trick question. That gives us 1, yep. And we'll note, by the way, that's in H. Right, that's a big thing to observe. This is in the set H. Now we'll move to this element, S, R, S. Now we know how to compose elements with each other. So we could flip, maybe flip these guys around. And we get S times SR cubed. And what does this give us? R cubed. Also in H. That's one of the rotations. So now we'll do it again. SR squared S. I'm just going down like the elements of H, right? So in the middle here, I'm just choosing a different element of H to put in. And then finding what we get. So SR squared times S, well, if I flip the R squared and the S, I just get SR squared, and that gives us R squared. We've done a lot of these actually computations already. And then lastly, SR cubed times S is the same as S times SR, and that gives us R. So as I've sort of switched out different elements of H, so I have S, H, S inverse, because S is its own inverse, what I produced was the subset H again. And what I want to show is that this is true no matter which element of G I pick. So we know it's true for the R elements because R's commute with each other. I know it's true for the S element, so we have just 3 more elements to go. So now let's try if G is equal to S times R. And we'll note that the inverse of SR is SR. We observed that in the example above. I'm going to skip the identity element because if the identity commutes with everything, so that's not really worth checking. You could check it on your own if you wish, but I'll check the other 3 elements. So if I do SR times R times SR, if we compute this product, or this composition, then we get, let's see, I'll flip those guys, I guess. So we get SR, I guess I'll call this guy SR squared, and then R cubed times S. And let's see, R cubed times R squared is R. And if we flip these around, we get S times SR cubed, which is R cubed. So that's in H. Let's try it with R squared. So again, I'm going to combine those middle R's, and I'll flip this guy around. So we have SR cubed times R cubed S. What is R cubed times R cubed? R squared. So we have SR squared S, and then we can flip these guys around. And of course the R squared and S actually commute. So R squared is the only rotation that does commute with S. And so we just get R squared. And one more to go here. SR times R cubed times SR. And that gives us, let's see. R times R cubed is just 1, right? So this is S times SR, and S times S is 1, so that just gives us R. So notice here, again, we just get the rotations back, right? And if we had conjugated with the identity, that would give us the identity element. So the last thing, and I guess there's sort of 2 other elements to go, but I'm going to have you check these. You can check G equals SR squared, and you'll find that SR squared times R times SR squared is, what did I get? I got R cubed, and that SR squared times SR squared is R squared, and that SR squared times R cubed times SR squared is R. So what's really important to notice is that while the operation is not commutative, right, it's not like when I conjugate R with the SR squared, I just get R back. It sent R to a whole different element. And that happens often, but it did not send it outside the subgroup. And so you could also take a minute and check the SR cubed if you like. You'll find that, again, you'll generate all the same elements of H. It won't send you outside of H. And so by checking these, conjugation, checking that this holds for every element in G, this is how we know that H is in fact a normal subgroup. So we spent a bunch of time yesterday working with the dihedral group of order 8, right, the symmetries of the square. And before that, we worked with, finding, defining what a left coset is. And we know that the set of left cosets partition a set. So they overlap, they don't overlap unless they're identical, right? And all the group elements are accounted for. Every group element will be in some coset. Just to remind ourselves, D8 consisted of these 8 elements, right? We have the 4 rotations, and then we have the reflection elements. So S, SR, SR squared, and SR cubed. And here they're saying, let's define the subgroup H to be the group generated by the rotations. So if we're just working with the rotation, the elements we can generate are these 4. Right, this is cyclic. And we kind of played around with these a little bit last time. So for the cosets, like we're finding left cosets. So basically what we're doing is we want to find the sets, G times H, which consists of elements, each one of these. We pick an element of G, and then we pick an element, G, of the overall group, and then we find these products. We let H range through all the elements of that subgroup. So here's our group H, just has the rotations. So if I take, for example, the 1 coset, if I take each of the elements of H and I just zap it with the identity element, what's going to happen?
They'll stay as they are.
Yeah, they're going to stay as they are. So this is just 1, R squared, R cubed. So that's the 1 coset. Now, since we know that the cosets partition the group, right, there's no overlapping. I don't have to find the R coset. If I find the R coset, I know I'm going to generate this. I don't have to find the R squared coset. They don't overlap unless they're identical. So what's the next coset I should try to find?
The S coset?
Yeah, like just pick an element that's not already in that one and start again. So the S coset, I'm just going to take S and zap it to like each one of these guys. So S times 1, I'll do this out the long way, S times 1, S times R squared, S times R cubed. And of course, that just really quite immediately gets us this coset, SR squared, SR cubed. Are there any other cosets that we have not found?
No.
Yeah, and so we got all what?
All 8 of the things.
Yeah, like every element in the original group is in one of these 2. So all elements are accounted for. And so that means there are just 2 cosets. Only 2 cosets of this subgroup. The coset depends on the subgroup that you're working with. Now, this subgroup that we found happens to be a normal subgroup. In fact, we spent quite a bit of time at the end of class on Wednesday showing that this was a normal subgroup. Remember, we found that, we did the conjugation of all the elements. So we found that no matter what element of G we picked, if we found G inverse, it always just gave us the same set. It gave us the same group right back, and we spent sort of painstaking few moments kind of trying to calculate that and show that every time we did this, no matter what element we picked, if I picked S and I did this conjugation of all the elements of H, I just got all the elements of H right back. If I picked SR and I did this conjugation with all the elements of H, I just got the elements of H right back. This is what it means for a subgroup to be normal. So we showed that H is a normal subgroup. And we've now just computed the left cosets of H. If H is a normal subgroup, then the left cosets form a group of their own. There are two left cosets. So when we say that the left cosets form a group, we're saying that if I take this element, the 1 coset and the S coset, they themselves are a group of order 2, right? I got 2 cosets. With this operation, if I take this coset, like an element of this coset, like the 1 coset, and I zap it with an element of the S coset, I will get an element of the 1S coset. Like you just do the operation on the elements themselves. And we call this the quotient group. And we would say that, and we refer to this group as G mod H. We write it kind of like a fraction. That's why we call it a quotient group. Some people call it a factor group, but I usually call it a quotient group. And we say that this group is G mod H. So let's find this quotient group. We know that H, the subgroup generated by R, is a normal subgroup. And so we can define this quotient group. We found the cosets. I'm just going to write them out again. So we have 1 R, R squared, R cubed, and S, SR, SR squared, and SR cubed. But if I'm doing operations with these cosets, or if I want to refer to a particular coset, usually we wouldn't. It would seem horribly inefficient and kind of cumbersome to have to write out the set every single time. We're kind of treating these as 2 different elements. So what we're going to do is just pick a representative element. We're going to say that this first coset, this is the 1 element, and I'm going to indicate that I'm not just talking about the 1 element in D8, but I'm talking about the 1 coset by writing it as with a little bar over. So that's the 1 coset, 1 bar. And this one, I'll pick S to be that representative, the S coset. You could pick either, right? Like you could pick any of the elements. I could call this the R coset, but it makes sense. If we're thinking of this as a group in itself, it makes sense to write the identity as 1 instead of as R. But technically, you could pick either one. So we would say that D8 mod H is equal to this set with 2 elements, each element representing the 2 cosets. Now, one thing that's sort of interesting to observe is that this group itself is cyclic. I could generate this group just using the S coset. Right, we'll note that S times S, this operation, when we say that when I perform an operation on 2 cosets, so if I'm using the bar notation, what this means is if I want S bar times S bar, I just do S times S bar. And of course now this operation here I can do in the original group itself. And we know that S times S is 1, and so that this is 1 bar. And so we get that element. So this is generated by that. What this says is a little bit more than just the fact that S times S is equal to the identity, which we knew was true in D8. What it says is if I take any element in the S coset and multiply it by any element in the S coset, right? So maybe SR and SR cubed, I will get an element in the R coset, in the 1 coset, I should say. How's that so far? This is not the first time that we've encountered this notion of thinking about, we didn't use the language of groups and subgroups and cosets and normal subgroups before. But we have seen this happen when we were working with equivalence classes and later on doing some, I think, some number theory. So here's a quick additional, this won't take much space, but an additional example. So think of the integers under addition. That's a group. And it's an abelian group, right? The operation itself is commutative, and if the operation itself is commutative, that means all subgroups are normal. So we'll take a look at the subgroup 5z. This is a normal subgroup of the integers, same operation under addition. And z mod 5z consists of these. We called them equivalence classes before, but they're the cosets. And we even use the same language. We've used the term z mod 5z, but now, that sort of jives with our some of the language we use in terms of groups and normal subgroups. So, one interesting thing about, this is only true with normal subgroups. Like, we can only mod out by a normal subgroup. There might be other subgroups out there, but if that subgroup is not itself normal, we can't mod out by it. And having a normal subgroup is a way in which we can actually create more groups from old ones. And that is one thing that sort of makes it more interesting. Questions before we keep going? Okay. So one result here says if we have a group and H is a normal subgroup, we already know that we can mod out and get another group, right? So we know already from what we saw on the previous page that G mod H itself is a group if H is normal. However, this theorem says that I could define a function from G to G mod H. And by which saying just send each element of G to its coset. And that's a homomorphism, and the kernel of that homomorphism is the subgroup H. Remember, the kernel of a homomorphism are all the elements that get sent to the identity. We call this the natural projection homomorphism. So let's return to our D8 group and the subgroup, the normal subgroup generated by R. So this function, phi, the natural projection homomorphism, oh, and I have a quick typo to fix here. This, instead of saying it goes from D8 to H, should be D8 mod H. So this says that the function should be defined in such a way that any element of G just gets mapped to its coset, right? The coset that it's in. So if we look back at the cosets that we had, here were our two cosets. So this says that any of the rotations should just get mapped to the one coset, and any of these other four elements should get mapped to the S coset. So that's just how we're going to define this. So phi of, I'll say, R to the I. So any of the rotations. This is just the one coset. And phi of any of the flips, S, R to the I, that goes to the S coset. You might see this written, you might see them written in the coset notation, so I mostly stick to the bar notation, but you might see folks write it as 1H and SH. They mean the same thing, they're just both referring to that coset. And notice all the elements that get sent to the identity, right? All the elements that are in the one coset. I'm going to scroll up again just briefly here. all the elements that are in the one coset, these are the elements of H. So that means that the kernel of this homomorphism is H. How's that so far? Okay. When we mod out by a normal subgroup, it's almost like saying, let's take this group here and kind of let it collapse on itself by way of this normal subgroup. That's what the natural projection homomorphism is. So now we get to kind of a big result. It's the first isomorphism theorem. There are actually four. We're only going to look at the first one. But it just says, suppose I have some suppose I have a surjective homomorphism of groups. So H is not a subgroup of G or anything, right? I just have a homomorphism that goes from one group to another that is surjective. So every element of H gets hit by something in G. It need not be one-to-one. Then the kernel of this homomorphism is normal in G. And G mod the kernel of phi, if we look at that quotient group, it's going to be isomorphic to H. So we already showed this in theorem 617. We spent some time proving this, so we won't kind of reinvent the wheel there. Was in theorem 617. So what we need to show is this part. We need to show that G mod the kernel of phi is isomorphic to H. So if we have to show that two things are isomorphic, what we need to do is we need to find the function. We need to define a function and then show that it is an isomorphism. So let's define this function. I'll call it pi. Pi is often used for like a natural projection homomorphism. So we're going to define this function. And for a little bit of shorthand here, I'm just going to denote, or I'll let K equal the kernel of phi, and that's a little bit quicker than writing kernel of phi every single time. So we're going to define a function. We'll call it pi from G mod K to H. And we will define it by this. We'll say pi of... Now, what are elements of G mod K? We're modding out by a normal subgroup. So the elements over here, the elements of G mod K, are the cosets. So we'll have pi of G bar, right, equal to, and I want to send to H. So the only thing we have that gets us from G to H is this phi function that's defined up here. So we'll let this be phi of G, not G bar, but G. Now there are three things that we need to show. Really there are four. One I'm going to leave and I'll put it up on Moodle, but I'm going to write it down because it really should be addressed. We need to show first, and this is the part that I'll just put up on Moodle, that pi is well defined. I'll put this on Moodle. Just means that it is actually a function. I mean, we could write an equation, but remember a function has to be something where if I plug in an element that can only go to one possible output, right? So because we're mapping an entire coset, we wouldn't want to just assume that that's a well-defined. We know, by the way, that pi does map into H because it takes pi of G bar and it sends it to phi of G, and phi of G is in H, right? Phi maps from G into H. So now the other parts, sort of the fun parts. We're going to show that we want to show it's an isomorphism, so we're going to show that pi is a homomorphism. What are the other two things we need to show in order for pi to be an isomorphism?
For an isomorphism, if it shows a homomorphism, it has 1-to-1 and onto.
Yeah, yep. So we're going to show that pi is 1-to-1. And then we'll show that pi is onto. Nice. Okay, so let's begin. We're going to show that pi is a homomorphism. So let's grab a couple of elements. You know, pi maps from G mod K to H. So we want to take a couple of elements over here in G mod K. So let's let, I don't know, G1 bar and G2 bar be elements of G mod K. All right, so I got a couple of cosets here. So now what we want to do is look at pi of G1 bar, G2 bar. What is it that I want to show? I mean, there's going to be a bunch of stuff in between, but like what, at the end of this process, what do I want to be able to write over here? Like, what is that homomorphism property?
Would it be that pi of G1 bar times, that equals pi of G1 bar times pi of G2 bar?
Yeah. So that's what we want, right? So just kind of putting this over here just to kind of keep our eyes on the prize. So let's begin by looking at the product inside. This is an operation between cosets, right? G1, the G1 coset and times the G2 coset. We know that this operation is defined by taking the coset of G1, G2 bar, right? We can just smash the G elements together and then take that coset. Now, how did we define the pi function? I'm going to scroll up briefly. We said that pi of a coset was just phi of the element, right? So, so we could write this as phi of G1 times G2. What do we know about phi? Let's sort of go back to what this theorem says. What is assumed true about phi to begin with?
That it maps from G to H.
Yep.
That it's a homomorphism.
Yeah, it's a homomorphism. So what does that allow us to do next?
Since phi is a homomorphism, we can split that up into the phi of G1 times phi of G2.
Yeah. And now, well, this lined up nicely. We're pretty much done. Phi of G1 is how we define pi of the G1 cosets, the G1 coset. And phi of G2 is how we define the pi of the G2 coset. I'm just going to write this a little bit less scrunched. So, you know, we started over here. We know it's equal to this. And that means that pi is a homomorphism. All right, so 1 down, 2 to go. We know pi is a homomorphism now. Let's show that pi is injective, or 1-to-1. Note that in our assumption about phi need not be 1-to-1, right? The only thing we know about phi is that it itself is surjective, but it need not be 1-to-1. So we're going to show that pi is 1-to-1. So we're going to start, we'll suppose, how we usually do these 1-to-1 proofs, we'll suppose that pi of G1 bar is equal to pi of G2 bar. What is it that we want to show? Right, we're showing that we're supposing that these G1 bar and G2 bar both get mapped to the same thing under this projection homomorphism, or under our homomorphism pi.
You're saying that G1 bar is the same as G2 bar?
Yeah, that's what we want to show. Yeah, so that's what it would mean if pi were 1-to-1, that we can't double up on outputs. So we're going to show that G1 bar is equal to G2 bar. Now, these are elements of G mod K. They are themselves cosets. So what we're really going to show is that G1 and G2 belong to the same coset. Like G1 as elements, not G1 bar, but like just as elements of G, G1 and G2 belong to the same coset. You know, half of writing this, you know, trying to figure out, half of writing this proof, or half of proving this theorem is just trying to figure out what elements are we dealing with? Are they G elements? Are they H elements? Are they cosets? And then what is it that we want to show? When we're showing this, we really want to keep in mind that G1 and G2, they're not just like individual elements, they are cosets. So, all right, let's see what we get. What is pi of G1 bar? How do we define that?
It's just going to be phi of G1.
Yep. So phi of G1, and then of course on the other side that would be phi of G2. So we're saying that phi maps both G1 and G2 to the same element in H. There's nothing wrong with that because, again, we don't know that phi is injective, and phi doesn't have to be injective. So, next, let's zap both sides by the inverse of phi of G1. So that would look like, let's see, let me make some space here. G1. What do we get on the left side? Yeah, right, we're multiplying an element by its inverse. So this is 1. And then on this side, just going to use the homomorphism properties a little bit. So we know that phi of G1 inverse, well, that's the same as phi of G1 inverse, phi of the inverse of G1, right? Like, it maps inverses to inverses, and then phi of G2. And I really should, if you guys don't mind, I'm gonna fix something here. It's gonna seem small, but it's kind of important because we don't know that these operations are commutative. We're not assuming that. So this, when I wrote this here, this factor, when I multiplied by phi of G1 inverse, really should have been over here because I have to multiply on the same side. I have to like left multiply or right multiply. So I'm going to fix that real quick and apologize for making you have to go back or fix anything.
What is the reason for that?
It's because the operation's not commutative. Like in regular algebra that we're used to, everything, addition and multiplication are commutative, so it's never mattered what side, like whether I add on the left or add on the right of this expression. But so if I'm multiplying on the left by this, I have to multiply on the left side by this. And just because the products won't be the same. So this should be phi of G1 inverse times phi of G2. One thing that you might have experience in that's not commutative is multiplying matrices. That's not commutative. And if you were multiplying on if you were trying to multiply on the left side by a matrix, you have to make sure you left multiply. You'll get a different product. So now we have this phi of G1 inverse times phi of G2. What else can I write because phi is a homomorphism?
Phi of G1 inverse times G2 inverse?
Yeah, G2, yeah. So phi of G1 inverse times G2 is 1. That's important. And by the way, that's why we picked the inverse, like the inverse of phi of G1, right? I really wanted to get the identity element over here. Because if phi of G1 inverse times G2 is equal to 1, does anybody know where that puts G1 inverse times G2? Like as an element of G. Right, I've got 2 G elements. I know this is in G somewhere, but I can be more specific than that, just knowing that it maps to the identity. What do we call the set of things that map to the identity element under a homomorphism? Any guesses in Randolph?
Is it an element of phi? That's probably wrong. I'm just gonna guess it.
No, well, it's not an element of phi because phi is a function and not a set.
Oh, okay. Is it an element of the universal set?
Well, sure, it's an element of the group, but we're trying to be a little bit more specific than that.
Is it the normal subgroup?
Well, what this is happens to be a normal subgroup, but it's a very specific subgroup.
I can't think of it.
It's the kernel. right? So the kernel is that's what we call all the elements that map to the identity. That's the kernel. And in this at the beginning of this proof, we said let's just abbreviate that as K. So now we'll take this sort of I don't know if I want to call it an equation because it's not an equal sign, but if we left multiply both sides by G1, then we have G times G1 inverse is 1. So on the left side now, we just have G2 is an element of G1 times K. Now G1 times K, that's a coset. Right? So we're saying that G2 is in the G1 coset. Another way of writing this, well, okay, let's see. I'll write that in English first. So G2 is in the coset G1 times K. And now we've mostly been using the notation, the bar notation. So what that means is that they're in the same coset, that G1 bar must be equal to G2 bar. And that's what we wanted to show up here. Right? Mission accomplished. And this means that pi is injective, or 1-to-1.
Obviously, this is a long proof.
Yep, it's pretty, I mean, there's a lot to prove. I mean, we have to write, we're writing 3 little mini proofs, right? Showing something's an isomorphism. Takes a lot of work.
And then we have to find the last one on Moodle.
Yeah, I'll throw that one up on Moodle. So our last bit that we're going to show is that we're going to show in class is that pi is surjective, or onto. So remember, just keeping in mind here that pi is a function. We know that it's a 1-to-1 homomorphism right now, but it maps from G mod K to H. And I want to keep this in mind. Knowing where it maps from and where it maps to is important when we're trying to show that something is surjective, because what that means is I want to say that no matter what element in my target group that I pick, right? So let's let H be an element of H. We want to show that there's some coset over here that maps to that under the pi homomorphism. So let's let H be an element of H. Now we're not gonna get there directly, like right away by using the pi function, but if we have an element of H, we can certainly find something that maps to H from G, not from G mod K, but from G. And we know that because in the beginning, the premise of this problem, of this theorem, is that phi is a surjective homomorphism. So we know at the very least there's an element in G that maps to H under phi. So because phi is surjective, then there exists some element G such that phi of G is equal to little h. Now we're ready to pull in the pi function, because phi of G is precisely how we define pi of the G coset, pi of G bar. This proof is very short. We grabbed an element of H. Look, here's a coset that maps to it under the pi homomorphism. So pi is surjective. How awesome is that?